Hello everyone. So far we have seen what is Euclid's division lemma and fundamental theorem of arithmetic. So using Euclid's division lemma, we got to know how to find HCF of given numbers, and using fundamental theorem of arithmetic, we got to know how to find HCF and LCM. Now let's continue. The next thing that we're going to discuss is about irrational numbers. Actually, we have already discussed what are irrational numbers in the first part of the video, that is the introduction part. So let's recall it again. What are irrational numbers? Basically, those which are not rational are irrational, right? So what are rational numbers? The numbers which can be written in the form of P by Q. For example, if I can write any number, for example, let's take 0.5, I can write it as 1 by 2. Therefore, it is a rational number. If there is any such number which cannot be written in the form of P by Q, if I cannot write it in this form, then such a number is known as irrational number. Or the other definition is a non-terminating and non-recurring decimal. Okay, in terms of decimal, it is a number, so irrational number. So what is irrational number? Non-terminating and non-recurring. Okay, meaning the decimal expansion, let's say 0.5, 1, 2, 3, 9, 8, 7, 6, 8, 4, 3, so on. If you observe, this decimal is, it goes on, right? It is not stopping, right? It is not terminating. So that's why we call it as non-terminating. At the same time, there is no pattern seen here. When I say pattern, it might be like this: 0.35, 35, 35, so on. See, a set of digits are repeating themselves again and again: 35, 35, 35. This is a pattern. Or it might be 1425, 1425, 1425, and so on. You can see there is a pattern. There is a set of digits repeating themselves again and again. But here there is no pattern as such. So these kind of decimals which are not repeating and which are not terminating, that is non-terminating and non-recurring, are said to be irrational numbers. Also, if you're not able to find square root or cube root of any number, that square root of number, for example, let's say root 2, can I find square root of 2? No. Therefore, this is a irrational number. Or let's say cube root of 4, we are able to find square root of 4, but we are not able to find cube root of 4. We cannot find it, right? So cube root of 4 cannot be found. Therefore, this is also an irrational number. This is also irrational number. If you're not able to find root of any number, square root, cube root, fourth root, fifth root, let it be any root, that root of that number will be an irrational number. Okay. Why can't we find it? Because cube root of 4 means what? A number multiplied 3 times should give you 4. Which number multiplied 3 times gives you 4? A same number. You cannot say 2 into 2 into 1. That's not possible, because this is a different from these two, right? All three numbers should be same. So there is no such number where if you multiply you get 4. Therefore, you are not able to find cube root of 4. Therefore, cube root of 4 is an irrational numbers. So these are the different types of irrational numbers, different types, or I cannot say different types, I would rather say different definitions. Okay, now we know that root 2 is not an irrational, is not a rational number, it's an irrational number. In this video we are going to prove it. Okay, why root 2 is not a rational number. Okay, that's why we are going to prove it. Let's take an important point for the proof. So we are going to prove that root 2 is irrational number. Okay, so we have to prove root 2 is an irrational number. Before this, there is an important thing which we have to know for the proof of this theorem. Note, let P be a prime number. Let's take a prime number. Let P be a prime number, any prime number. If this prime number, if P divides a square, where a is any composite number or any number, in general it can be any number, okay. If P divides a square, it implies then P also divides a. A very important thing. If a prime number divides a square, a can be any number. If P divides a square, then P also divides a. For example, we know that 3 divides, 3 is a prime number. See, I'm going to take only prime number. 3 divides 36, right? 3 divides 36. 36 is nothing but 6 square. So 3 divides 6 square. Definitely 3 will also divide 6, isn't it? So your a is 6, a square, a. Okay. Similarly, 5 divides 25. 25 is nothing but 5 square. If 5 divides 5 square, 5 also divides 5. Or let's take 7 divides 49. 49 is what? 7 square, right? 7 divides 7 square, obviously 7 divides 7. Or let's take 2 is a prime number which divides 64. 64 is nothing but 8 square. If 2 divides 8 square, 2 will also divide 8, isn't it? 2 divides 8. So this is the important note. Okay, if P divides a square, where P is a prime number, very important. You should only select prime numbers. If a prime number divides a square, it also divides a. Okay, very important thing. The other important thing is, if a number, let's say, for example, if 2 divides some number, or let's take an example, 78, is this divisible by 2? Yes, of course, it's an even number. It is divisible by 2. Or in another words, I can say this is a multiple of 2, isn't it? Because this 78 can be written as 2 into 39, isn't it? Now, this 78 is divisible by 2 because it is a multiple of 2. That is one way. Or I can also say this is an even number. That is why it is divisible. Let's take another example. 78, is this divisible by 3? Yes, it is divisible by 3. You can check it out. It is divisible by 3. Why? Because this 78 can be written as 3 into, it is a multiple of 17, right? So it is 3 into 26. It is a multiple of 3. So meaning 78 can be written as 3 into 26. So that's what I'm saying. 78 is multiple of 3. Okay. Or let's say, let's take 65. Is it divisible by 3? No, because 65, you cannot write it as 3 into something. Any number, you take any number, it's not possible at all. Okay, that is why 65 is not divisible by 3. In other words, this 65 is not a multiple of 3. In 3 tables, you won't get this 65. So meaning, if a number is divisible by 3, then I can write 3 into something. Here in this case, 78 is divisible by 3. Therefore, 78 can be written as 3 into something. That something here is 26. Or let's take 45. Is it divisible by 3? Yes, it is divisible by 3. Therefore, I can write it as what? 3 into 15. So in general, if a number is divisible by a, let's say, let's not put it in general way. Okay, let's just take particular example. If 2 divides, let's say, some 36, 2 divides 36, right? Therefore, 36 can be written as what? 2 into something. That something is 18 over here. In similar way, observe, instead of a number here, let me write P, or let me write A. If 2 divides A, then this A definitely can be written as 2 into something. That something I'll take it as K. Isn't it? That's what we did. 36 is divisible by 2. What did we do? 36 can be written as 2 into something. Something is 18 over here. It's an integer. Okay, here it is 18. Similarly, if 2 divides a number, then this number should be expressed as 2 into something. Okay, similar way, if 3 divides A, then definitely this number A can be written as 3 into something. We don't know what is that because we don't know what this number it is. So it depends on this 3 into K. For example, what did I do? 78 can be written as 3 into 26. 45 can be written as 3 into 15. So these numbers are divisible by 3. If they are divisible by 3, then 3 into something. Here we don't know what is that something, so we have taken it as K. Okay. These two things, if you know this properly, if you have understood, it's very easy to understand the proof of this irrational number. So let's focus on that. Okay. Let's start the proof. We're going to prove it using a method known as contradiction method. What is this contradiction method? I hope you know the meaning of contradiction. Okay. So here we assume something. Initially, we start with something. As and then we proceed with the problem. We get an answer or we end in a step where the answer or whatever we have got is in contradiction with the earlier assumption. Okay. Let's do that. So we're going to prove this by contradiction method. That is, I have to prove root 2 is an irrational number, but we'll assume it is a rational number. Let us assume, coming to the proof, let us assume root 2 is irrational number. Let us assume root 2 is irrational number. Sorry. It is a rational number. If it is a rational number, every rational number can be written in the form of P by Q, isn't it? Therefore, root 2 can also be written as P by Q. What are this P and Q? P and Q are integers and also co-prime. What do you mean by co-prime? They don't have any other common factor other than 1. The last video I told you what are co-primes. Two numbers are said to be co-primes if they don't have common factor other than 1. For example, let's take 3 and 8. Which is the number that divides both 3 and 8? It is only 1, isn't it? Other than this, there is no number which is going to divide both. So 3 and 8 are said to be co-primes. Okay. Another example, let's take 3 and 5. Or I cannot say 3 and 15 as co-prime because these two numbers are divisible by 1. They're also divisible by 3, isn't it? Both these numbers are divisible by 1 and also by another number. Numbers are said to be co-prime if they have only one number as common factor, that is 1. Okay. For example, let's take 2 and 15. These two are co-prime because the only number that divides them is 1. Other than this, there is no other number. Okay. Which means here P and Q are co-prime, meaning that is, let me write it in the bracket. That is, P and Q do not have any common factor other than 1. So other than 1, they do not have any other common factor. Okay. Now, let me square it on both sides. Squaring on both sides. So what do we get? Root 2 the whole square is equal to P by Q the whole square. So square and root gets cancelled. You're left with 2. 2 is equal to P square by Q square. Okay. Now let me cross multiply it. So I get 2Q square is equal to P square. In other words, I can write it the other way. I can write it like this. P square is equal to 2Q square. Now focus this. P square is some number, okay? that number is written as 2 into q square. Meaning it is like this, right? Earlier I gave you an example. 36 is divisible by 2. Therefore, 36 can be written as 2 into something. That something is 18 over here. Observe, this is following the same pattern. There is a number which is written as 2 into something. Meaning this number should be divisible by 2, isn't it? Therefore, it implies 2 divides p square. Okay, 2 divides p square. If 2 divides p square, it will also divide p. Implies 2 divides p. Okay, I had given you the other example, right? P divides a square implies p divides a. Okay, now instead of a, here you got p. The prime number that I have taken is 2. If 2 divides p square, 2 will also divide p. Okay. Now, if 2 divides p, it means that p can be written as 2 into something, right? I'll take that something as k. See, if this p is divisible by 2, obviously p should be written as 2 into something. That something I've taken as k. Okay. Let me substitute. Let me take this as equation 1. Let me substituting the above result in 1. Okay. So p square is equal to 2q square is the equation 1. Okay. In place of p, I can write it as 2k the whole square is equal to 2q square. 2k the whole square is 4k square, which is equal to 2q square. Okay. I can send this 2 to this side. So it becomes 4k square by 2 is equal to q square. So 2 ones are 2 twos are. Let me continue here. Therefore, what have we got now? 2k square is equal to q square, which implies, or I can write it in another way, q square is equal to 2k square. Now observe, q square is also some number which is written as 2 into something, meaning this q square is divisible by 2. 2 divides q square. Same pattern. P square is equal to 2q square. Then what did we conclude? P square is divisible by 2, or 2 divides p square. So 2 divides here, 2 divides q square implies 2 also divides q. Now observe the contradiction. Okay. What did we assume earlier? That p and q are co-primes, isn't it? Now we assumed it as a rational number. That is why we got this p and q, isn't it? We took this as a rational number. That is why we got this p and q. What is this p and q? Co-primes, meaning both are divisible only by 1. Both are divisible only by 1. There is no other number which is going to divide them. But observe here, 2 is dividing p, it is also dividing q, which is a contradiction, right? What did we assume? We assumed it as a rational number. Therefore, we got this p and q. What are this p and q? Co-primes, meaning both are divisible only by 1. There is no other number which is going to divide them. Due to our assumption, we got this. That is, there is no other number which is going to divide these two. But what did we end with? We got a number that is 2, which is dividing q, which is also dividing p. Okay. This is a contradiction. Hence, therefore, why is this contradiction? Because of our assumption. What was our assumption? It is a rational number. If this is wrong, what is correct? Root 2 is an irrational number. So this is how we prove root 2 is an irrational number. Let's take one more. Let's prove root 3 is an irrational number. Okay. So let's prove that root 3 is an irrational number. Again, the same thing by contradiction method. Let us assume root 3 is rational number. So if root 3 is rational number, every rational number can be written in the form of p by q. What are p and q? P and q are integers, or in general, I can write it as co-primes. Okay. Co-primes itself makes it to be an integer. Okay. So p and q are co-primes, meaning there is no other number except 1. Only 1 is the number that is going to divide p and q. Both p and q are divisible by 1. Okay. Together, Individually, they are divisible by many numbers. See, don't get confused. See, 4 and let's say, let's take 15. See, these are co-primes because together both the numbers are divisible by only 1. But individually, if I take only 4, it is divisible by 1, it is divisible by 4, it is also divisible by 2. If I individually take this, it is divisible by 1, 15, then 3, then 5. There are so many numbers. But which is the only number that is common? Only 1. Okay. So 1 is the only number that divides both 4 and 15. Other than this, there is no other number. Therefore, 4 and 15 are called as co-primes. So in the same way, P by Q are co-primes, meaning both are divisible by only 1. So let me square it on both sides. So what do we get? Root 3 the whole square is equal to P by Q the whole square. So square and root gets cancelled. 3 is equal to, since the things are in division, I can split the powers. P square by Q square. Cross multiply, we get 3Q square is equal to P square, which implies I can write it as P square is equal to 3Q square. Now observe, this P square is a number. It is some number. It is a value, right? P is some number. So P square will give you some number. This number is written as 3 into something. Okay, which means this P square is divisible by 3. Okay, therefore, which implies 3 divides P square. If 3 divides P square, 3 will also divide P. 3 divides P. If 3 divides P, then P can be written as what? 3 into K. Okay. Now substituting this in equation 1. Substituting in 1. The above result in 1. 1 is P is equal to 3Q square. So P is 3K. 3K the whole square is equal to 3Q square. So how much do we get? 9K square is equal to 3Q square, which implies you get this 3 the other side. 9K square by 3 is equal to Q square. 3 ones are 3 threes are. Therefore, Q square can be written as 3K square. Again, same logic. Q square is written as 3 into something. This is possible only when this number is divisible by 3. So therefore, 3 divides Q square implies 3 divides Q. So what did we assume? That there is no other number except 1 which is going to divide P and Q. But what did we get here? P is divisible by 3. It is also divisible by, Q is also divisible by 3. P is also divisible by 3. Okay. Therefore, they have got common factors other than 1, which means this is a contradiction. We assume something, the result we have got is opposite to the assumption. Okay. Therefore, this is wrong. If this is wrong, what is correct? Root 3 is rational is wrong. Therefore, the correct thing is irrational number. Okay. So this method we call it as contradiction method. A very important question from the exam point of view. Let's solve few more problems based on this. Okay, the next question, prove that 3 plus 2 root 5 is an irrational number. That is, actually 3 is a rational number. Okay, 2 root 5 is actually irrational number. Okay, the combination 3 plus 2 root 5, we have to prove it is an irrational number. Again, we are going to solve this by contradiction method itself. Okay, that is, we are going to assume that this number is a rational number. Okay, let's assume proof. Let us assume that 3 plus 2 root 5 is rational number. Okay, if it is a rational number, it is very obvious that 3 plus 2 root 5 can be expressed in the form of P by Q. What are P and Q? P and Q are co-primes. P and Q are co-primes. Very, very easy stuff. Now just observe. I'll try to retain this root 5, meaning I'll try to send all the other numbers the other side except this root number. Okay. First, let me send this 3 to the other side. So you get 2 root 5 is equal to P by Q. minus 3. Let's take LCM. Okay, so 2 root 5. It's very obvious. What is the LCM of q and 1? It is q itself. So it becomes p minus 3q by q. If you don't know how to take LCM between numbers and alphabets, you can go with the shortcut trick. That is, you multiply the denominators, q into 1 q, crisscross, p into 1 p, q into 3 3q. You can also apply that. Okay, now let me transpose this to this side. It's in multiplication. If it comes this side, it will become division. Root 5 is equal to p minus 3q by 2q. Now observe carefully what we have got. We have got root 5 is equal to p minus 3q by 2q. Okay. Now, so far in the previous section, we have known that root 2, root 3, we proved it, right? Just now we proved that root 2, root 3. Similarly, same procedure, you can also use it to prove that root 5 is an irrational number. So all these are irrational numbers. We know how to prove that is irrational. Now observe, p is an integer, 3q is also an integer. It's very obvious. If you multiply an integer by integer, you get back integer itself. Okay, and if you subtract integers, you get back integers itself. We also call it as closure property. Take any two integers, you add them or multiply them or subtract them, you will get back integers itself. But if you divide, you won't get back integers. Okay, let me repeat it. Take any two integers, add them, you get back integers. Multiply, you get back integers. You divide it, you get back integers. Okay, now observe, but if you divide, you won't get back integers. For example, 2 is an integer, 3 is an integer. If I divide it 2 by 3, it is not an integer, it's a rational number. Okay, that is what I said. If you add two integers, you get back integers. Multiply, you get back. Subtract, you get back. But division, you won't. Okay, similarly, observe, p is an integer, this is also an integer. Integer minus integer, you get back integer. Okay, some integer. Okay, let's say k. This 2q, let me write it as m. Okay, this is also an integer, right? I'm just giving it a new name. Just observe, I've got integer by integer, that is a rational number. Integer by integer is what? A rational number. Okay, so in the RHS, the right hand side, I've got a rational number, but we know that root 5 is irrational number, isn't it? So how can a rational and irrational be equal? This is not possible, right? So there is a contradiction. What is a contradiction? This is an irrational number. What I've got here is a rational number. How do I know it is a rational number? Because the numerator is an integer, denominator is integer. Usually what is p by q, where p and q are integers, right? So this entire thing is integer, this is also integer. So integer by integer, which means this is a rational number, whereas this is an irrational number. How can an irrational be equal to rational? This is wrong, right? Why is this thing arising? It is because of our assumption. What was our assumption? That this is a rational number. So this assumption is wrong. Therefore, the correct thing is 3 plus 2 root 5 is irrational number. This is a contradiction. This is a, or let me write it clearly, p minus 3q by 2q is a rational number, whereas root 5 is irrational number. This is a rational, but root 5 is irrational. Therefore, this is not possible, which implies our assumption is wrong. Our assumption is wrong. Therefore, 3 plus 2 root 5 is irrational number. Okay. Our assumption was rational. If it is wrong, the correct thing is irrational number. Very simple. We assumed it as a rational, so we can write it in the form of p by q. We solved it for root number. Okay, we have got this. This is rational, but we very well know that it is irrational because just now we proved it, right? Root 2, root 3. Follow the same procedure. You will also end up root 5 is an irrational. This is an irrational, but this is a rational. Therefore, if this is rational, this is irrational. They cannot be equal. There's a contradiction. Why? Because our assumption is wrong. If this is wrong, what is correct? Irrational number is correct. Okay. So this is the way that you prove a combination of rational and irrational. This is rational, this is irrational. Together, how do you prove? Using this logic. Okay. Let's continue with some more problems. Okay, let's take another question. Prove that 2 minus 7 root 5 is a, or let's take 7 root 3 is irrational number. Same thing. Let us assume 2 minus 7 root 5 is rational number. If it is rational number, then it can be written as P by Q. Send this 2 to the other side. See, remember the one mistake that most of you do is we are transposing this 2 to the other side. This is positive 2. If it goes this side, it will become minus 2. Now this minus remains as it is. Okay. So most of you neglect this. Then it will be wrong. Okay. Let's retain it as it is. Minus 2. 2 can be written as 2 by 1. How to take LCM? Or the shortcut, Q into 1 Q, P into 1 P, minus 2 into Q is 2Q. Minus 7 root 5. Okay. Therefore, root 5 is equal to P minus 2Q divided by, get this minus 7 to the denominator. Again, same logic. This is an integer. The below thing is also integer. Integer by integer is a rational number. This is rational. I'm sorry. This is root 3, right? Doesn't matter. So this is rational, whereas root 3 is irrational. We have proved it. So irrational cannot be equal to rational. There is a contradiction. Why did this happen? Because of our assumption. What is our assumption? It is rational. It is wrong. Therefore, this becomes an irrational number. I hope that you have understood how to prove irrational numbers. Thank you, students.